Continuing with the cumulative multiple choice review, this is 29. So here's the problem. Got cut off, so I had to write it in here. The figure above shows the graph of a twice differentiable function g. So that just means twice differentiable just means the smooth curve. So here's our g graph, and the line tangent to the graph of g at the point 0, 3. So this line shares the same slope of the curve at the ordered pair 0, 3. Okay. So the question says, find the value of the limit as x approaches 0 for g of x e to the negative x minus 3 over x squared minus 2x. So anytime we see a limit expression that we want to evaluate, we just plug in that 0, see what that gets us. So we plug 0 in for x here. So let's go back up here. When I plug 0 in for x, I get g of 0 times e to the 0 minus 3 over 0 squared minus 2 times 0. So g of 0 is 3, right? That's the y value of the g graph, so that's 3. 3 times 1 is 3, 3 minus 3 is 0, so we get 0 over 0. Again, indeterminate form indicates that there is a limit that exists, but right now we are at an incomplete stage. So the way we get that 0 over 0 resolved is we're going to apply L'Hopital's rule, which means we're going to find the derivative of this numerator expression, and then separately we'll find the derivative of the denominator expression. And once we find the derivative for the numerator and denominator, then we can reevaluate, and hopefully that will lead us to a real number. So if we want to find the derivative of the numerator expression, we know the negative 3 goes to 0, but the g of x e to the negative x, these are distinctly separate expressions that are being multiplied together. So if we want to find the derivative that has terms that are related to one another by multiplication, then we have to go through product rule. So product rule says f prime times g plus f g prime. So f prime is the derivative of g. That's just g prime. And then the original g function, e to negative x, stays e to negative x. Go back to f, so our original function here stays. And then the derivative for e to the negative x is e to the negative x times negative 1. Okay. Again, negative 3 goes to 0. And then we move to the denominator. Denominator is a separate expression, so we're going to find its derivative. X squared becomes 2x. Minus 2x becomes negative 2. And then once we have our derivative form of our original expression, we're now going to reevaluate. So now we're going to re-plug in 0 in for all the x's. So g prime is 0, e to the 0, g of 0 times e to the 0, and over 2 times 0 minus 2. So g prime of 0 is basically saying, what is the slope of the g graph at 0? Well, we don't have a equation for us to find the derivative, but what we do have is we do have this tangent line. So if we can figure out the slope of this tangent line, then the slope of that tangent line is going to be the exact same slope of the curve at that point. So I just picked 2 points on this line here, and if I do rise over run to figure out slope, right, g prime of 0 is just the slope of the tangent line. I can go rise over run, so up 2 over 1, that's the slope of 2. So I know that g prime of 0 is the slope of the tangent line, which is going to be 2, times e to the 0 power, that's 1. G of 0, we said before, was 3, that's just the ordered pair, times negative 1, which is negative 1, all over 0 minus 2, which is negative 2. So 2 minus 3 is negative 1 over 2, that's, negative 1 over negative 2, so that's 1/2, so that's our answer choice B. Right, moving on to 30. We have a function defined by g of x is the definite integral from 1 to x of this expression here. At what value of x does g attain a relative maximum? So relative maximum can be found by taking g prime or finding g prime and then using the g prime expression to sketch and figure out the x-intercepts, right? So what we can do is let's first find g prime based off of this. Now g prime is the derivative of this expression. So this integral tells us that this expression is right now sitting above this, what we see here. So if we find the derivative of this integral, that's going to basically eliminate this, and bring us down to this expression. Okay. In other words, if the antiderivative of this expression brings us to g of x level, then this expression that we're staring at is really basically just the g prime level. We can also apply second theorem, which just says that if I find the derivative of an integral, these two operations undo each other. I just plug in my upper bound in for the variable, and when I do that, I'm just left with what's inside the parentheses. So here's my g prime, and if we sketch g prime into our calculator, and this is what our g prime graph looks like if we enter it in our calculator. Basically, our x-intercepts is going to be places where a potential relative max or relative min can occur, because that's on a g prime graph, x-intercepts is going to translate to a slope of 0 on the original graph. Anything above the x-axis represents positive slope, anything below represents negative slope. So if you have a positive slope hitting a 0 slope followed by a negative slope, then that graph is going to resemble a relative max. So relative max is going to be at 0.471 because slope changes from positive to a negative slope, right? If we look at a relative maximum, the slope goes from a positive, which is shown here, goes to the slope of 0, that's here, and then negative slope to the right of 0.471. Okay, so answer choice A. All right, 31. Select values of the differentiable function h and its derivative are given in the table. Let f be the function defined by f of x equals the definite integral from 0 to x of h of t dt, which is the least possible number of critical points in the interval from 2 to 13. So we can find critical points by setting f prime equal to 0. So f prime is basically just the h of t, right? If the antiderivative of h brings us up to the f of x level, then the h of t must be sitting at the f prime level, right? So our f prime is really the h of x. Okay. So let's sketch a potential f. So h of x is basically f prime. So I'm going to just put these order pairs onto my graph and call it f prime. And I have 16. I have 2, 16, 6, negative 8. So I'm just looking at this row here. I'm not looking at the h prime. This is just there to throw us off. We're just looking at the h of x graph. Okay, so here's our h, and based off the fact that this is a differentiable function and that all the points must be connected, the least number of times that our graph is going to hit the x-axis, or basically have a slope of 0, is going to be 2 of these points, right? Maybe there's more that we don't see, but it's asking what is the least possible number of critical points where h prime is equal to 0, which is basically f prime. The only way that if we connect all these points here, the least number of points that will hit the x-axis and still allow us to connect all these points, the least number is 2. All right, 32. We have a piecewise function. It's given here. What is the value of the definite integral from 0 to 8? Okay, so I think the easier way to go about doing this is just to sketch these graphs out. Now, these are all just horizontal lines. This is y equals 2. You got y equals 3. You got y equals negative 1. All right, so in other words, f of x is just y equals 2, y equals 3, and y equals negative 1. So these are easy to sketch because these are all just horizontal lines. So we want a horizontal line at y equals 2 from 0 to 2. So I sketched that here. That's a horizontal line there. And then I have another horizontal line that jumps up to 3 between 2 and 3. And then I have another horizontal line, y equals negative 1, from 3 all the way to 8. So if I want to find the value of the definite integral, then I'm just looking at the region between the x-axis and that line. So all these are going to form rectangles of various shapes, of various widths and height. So really, definite integral, if I just find the area of these rectangles and then just add them up, And then keep in mind that negative regions will give me negative values. So this is 2 times 2, which is 4. This is 1 times 3, which is 3. This is 5 times negative 1, which is negative 5. So if I add these up, I get 4 plus 3 minus 5. 7 minus 5 is 2. The other option is we can go through and do power rule for each of these terms, which I think will take longer, but it's definitely a possibility. I'm taking the depth integral of 2 from 0 to 2. I'm taking the depth integral from 3 from 2 to 3. I'm taking the depth integral of negative 1 from 3 to 8. And if I set it up this way, we can see that we can do power rule for each of these terms. Then we can evaluate our upper bound minus lower bound. 3 becomes 3x, upper bound followed by lower bound. Negative 1 becomes negative 1x, upper bound followed by lower bound. Total all those values together and we get the same result. Just a lot more writing to do, but it's the same result.